So Martin Bollman from Setf Group, who was also part of the TP2, will talk about criticality metrics and the identification of criticality phenomena.
Thank you. Hi. So we had a lot about criticality, and the question is, what is criticality? Is this critical? There is a pedestrian coming from the right side. It's similar to those functional use cases we have seen before. It looks critical, but I can tell it's not. You can click the link if you see the PDFs later, see the video in the internet. It's not critical, but it looks critical. We have investigated in a lot of scenarios. Here we see 3. I wanted to play them as a video, but this takes too much time, so just the screenshots. We have in the upper left something similar to this pedestrian crossing scenario. This purple cube is a pedestrian stopped shortly before him. Up on the right, it's a left turn from the oncoming traffic. It's in my eyes not critical, but it is in the criticality database. And we have on the lower left, we have pedestrian we hit by a car, but this scenario looks not critical when I see this in original, but there was a crash. So at the end, it's not just if there is a crash or not. This is not a measure for criticality. So we can see here the near crash, upper left is no crash, but I would assume it's a high criticality, so the belly criticality. Upper right, near crash with car, no crash, and criticality I would assume is low. But on the lower left, criticality is high. I would assume it's medium. So what is medium? But I would assume it's medium. But there was a crash. So the challenge is, how can safety of a driving intelligence or driving circumstances be assessed? Assessing driving intelligence or driving circumstances only in terms of the number of accidents would be too trivial as an approach. After all, the near accidents also can be a strong indication of minor driving intelligence or bad driving circumstances. And driving circumstances, I think, is something like that what we have got explained by a criticality phenomena. So at the end, we investigated and reviewed, analyzed, and developed criticality metrics in VV methods and summarized them. This is a rough overview. If you wanted to see this in detail, you can go to the poster 9.3, I guess. Christian introduced it. But just shortly, we have grouped them into simple measures based on the equation of motion, trajectory-based, potential-based, and rule-based measures, but figured out that the rule-based measures on the right side are not sufficient for us, as they are not able to detect unknown scenarios. As if they are rule-based, I have to have a rule, and if I have a rule, I have to know the scenario. So they can't be used for unknown scenarios. This is why we are focused on the 3 left ones. So, and to be honest, this is the end of the presentation for criticality metrics, because we want to do more with criticality metrics. We want to use them for identification or for analyzing criticality phenomena. And that we have done by using this well-known scenario with pedestrian crossing and occlusion. We have seen it in Christian's presentation. I think we have seen it before in Christoph's presentation too. We have this scenario, pedestrian crossing, we coming from the left. There are occluding vehicles and bicyclists, or in our scenario, a pedestrian is coming behind this occluding street from down to up, want to cross the what was it called? The pedestrian crossing behind this occlusion. And we have set up, we have logicalized this scenario by saying the ego vehicle has velocities between 2 and 30 kilometers per hour. The pedestrian has velocities between 1 and 10 kilometers per hour. And we have a coordinate where we would hit the pedestrian if there is no action, no reaction from the ego vehicle. So if we didn't hit the brake or didn't steer beside, we will hit him with 1 meter to the left, which is the left mirror, 1 meter to the right, which is the right mirror, or something in between. And depending on those 3 parameters, we have defined the starting position of the ego, so that we would hit the pedestrian in each scenario if there wouldn't be any reaction. And in addition, we have defined 3 phenomenon parameters, where the first one is the occluding distance, 0 meters is all the vehicles are standing right next to the pedestrian crossing, and 11 meters is they are 11 meters far away from this pedestrian crossing, which is less occlusion. We have modified the friction coefficient between 0 and 1, and we have modified the visibility due to fog between 40 and 170 meters. And we got this. This is what we call the criticality density cube. Each point is one simulated scenario, so everything was simulated in a simulating toolchain. Each point, one simulated scenario. The color is yellow is high criticality, where we see pure yellow, it was a crash, it's assumed as a crash. Orange is a near crash, blue is no crash, and purple is not complete uncritical, but yeah, don't think about it. We see the scenario picture blended in just to analyze this cube a bit better. We see this axis is the faster the ego, the more critical, because we have less reaction time, of course. The faster we are driving, the less reaction time we have. This is one you can experience at our driving simulator there at poster 9.3, where we have two maximum speeds, 30 or 50 kilometers per hour. And if you try it, you will see if you are driving faster, you have less reaction time. We can see the faster the pedestrian from low from the lower part to the upper part of the cube, the faster the pedestrian, the more critical, because the less we have reaction time. And we can see the more the pedestrian will be hit by the near side to the near side, it's more critical because we have less reaction time. So far, so simple. We can see two other things. We have this area on the upper edge of this cube where we see there is a huge yellow region, which is due to an anomaly of this used criticality measure, where the pedestrian crosses shortly before the stopped vehicle, and we have an interference between two potentials. There was a potential measure used, and those two potentials are intersected, and therefore we have a high criticality without a crash. It's perhaps an anomaly to the criticality measure, but it can even be a criticality, or it can be an anomaly to the driving function too, could be. And the other thing is this noise we can see in those points. This is because we are here just able to analyze or to visualize 3 parameters plus the criticality as a 4th parameter, but we have in fact 6 parameters where we have for each criticality phenomena parameter 1 dimension 2, and this is why we see this noise. A blue beside a yellow point could be that this yellow point is measured with low friction coefficient and the blue one with a high friction coefficient. So the parameters of the equation of motion could be the same, but the one time I have no friction or less friction, and the other time I have high friction, and this is why they have different criticalities. To identify now the criticality phenomena, because in this cube 100,000 samples are analyzed with all criticality phenomena, and we aren't able to identify the influence of each criticality phenomenon. We have filtered those cubes, and make it that way. We have filtered those cubes and categorized it like this table showed below, above. We have one cube without any criticality phenomenon here to the left, and then they are increasing to just visibility, occlusion, friction, combined visibility and occlusion, combined visibility and friction, friction and occlusion, and on the right side, the most right, all criticality phenomena are combined together. And we can see how, so yellow is high criticality, and we can see how criticality increases from without phenomena per phenomenon to the most yellow space-filling cube on the right side where all phenomena are combined. We can put this into measures. We can see here on the left side, it's the average criticality, it's really less. And then we can see how it's rising. So we can not just see that each criticality phenomena has an influence to this scenario. No, we more see how huge this influence is and which phenomena is more critical or less critical. At the end, we have done all these analyses with all those measures I introduced in the first part of my talk, and we can see that the coloring, so the grade of all these colors is different, but at the end we see always the same picture. It is every time that without the criticality phenomenon, we have the less average criticality, and the more criticality phenomena I take into account, the average criticality is rising over all measures. Which leads at the end to my conclusion, where we say that we have an effect. So all criticality phenomena, this is the first important point, all criticality phenomena have an influence to the criticality density, and therefore all hypotheses regarding criticality phenomena are true. All used measures are able to show the effect of each criticality phenomenon, and the crash regions, beside. The rest you can read in the handout too. So I think we have shown that we can use criticality metrics to identify and to verify criticality phenomena. So this is my talk.